It's our great honor to invite Professor Giorgio Parisi joining this panel discussion. And we are also honored to have Dr. Bai, the head of Theory Research Lab, joining this discussion. My name is Jui. I'm the head of Lagrange Mathematics Research Center. The first question is more on a broader view. It's about the relationship between mathematics and physics. Everybody knows you were awarded the Nobel Prize in Physics in 2021 for your pioneering work on disordered complex system, beginning from 80s. And in your opinion, what has been the most important development in statistical physics over the past few decades?
Thank you for this interesting question. I think that one of the most interesting things that happened in physics in the last 15 years was the ability to understand the behavior of a very large collection of agents. Now, the thing that was happening with the renormalization group with Ken Wilson, Kadanoff, and others here was to understand the ability of emergent phenomena in a collection of agents which were homogeneous. And this led to the normalization group and the full understanding of standard ferromagnetic transition and many other type of transition. Now, the point that came that was very difficult to go on was the situation where the agents were not the same. Therefore, the system was not homogeneous. You have agents which behave in a different way, and which, in the language of people doing physics or mathematics, they call disordered system. Disordered system because there is an intrinsic disorder in the cell. Now, there are some techniques that can be used relatively easy if the disorder is not strong or if the disorder in some sense does not change too much the things with respect to the standard models. But however, in disordered system, there are new phenomena that were not expected in advance. For example, the most famous one is localization, and localization was the theory of localization was done by P.W. Anderson, and for which he won the Nobel Prize at the end of the 70s. Now, the things happen that you have many other types of phenomena for which you are of simple statistical mechanics, because localization is a quantum phenomenon, but you have already at the classical statistical mechanics level, you have other phenomena, and these phenomena happens very often when there is some frustration in the system, which means that you have that different agents have different requirements that are not compatible one with the other one. And all the things that happen that in this case you need to have a compromise. And what happens that when you go look to this system, it means that you have to do a compromise also in the global system. And from the point of view of equilibrium, this system, there are many, many different types of realization. This is something that came out from heuristic computation doing the standard method of physicists, but this heuristic computation were more unsafe from the mathematical viewpoint than the standard one, because they were starting they had to use a new technique that are not very well founded mathematically, if the result were correct or not correct. Because although I did this type of computation myself, I was not 100% sure that the result was correct, because the point was the following, that the naive computation will give a result which was a 3% error, with an error of 3%. The computation that I did was in agreement with computer data and so on of a part of 1000. It could be also possible to was the first step of a sequence of a more and more complex type of approximation, which I was not able to find. But in the end, what finally turns out that with the work of mathematicians, they were able to prove that the result was correct. The thing was really impressive because I never believed that the thing can be proved mathematically, because the type of approximation that one was doing was very strong. Not really the approximation, the hypothesis. One was doing some choosing some simple answers.
The theory of spin glasses seem to act as a bridge between mathematics and physics. And in the field of theoretical computer science and statistics, there have been attempts to rigorously prove many conjectures made in 80s by statistical physics and in the last century, okay, such as those by Professor Michel Telegram, a recipient of the Abbe Prize recently, and also the traditional math schools in Russia always believe mathematics and physics are the two sides of one coin. And how do you view this relationship between mathematics and physics?
And in the end, the thing was really impressive what mathematicians have been able to do, because first all they started with Francesco Guerra, that was able to prove that my result was a lower bound, that the real value was higher. And after there was another Lagrange that was to prove the things in the other direction. So the things was the correct one. However, the Lagrange proof was somewhat complex. I remember I tried many times to read, but I understood for a few minutes. But after, I was never able to redo after 1 hour, 2 hours the argument. And in the end, the things was really simplified by the people, other mathematicians, especially by the work of Panchenko, which were able to show that the main hypotheses that one is doing were correct. They can be derived from first principle. So the thing that concerning the last question that you were saying, the role between mathematics and physics, I think that you are right that they are the two sides of the same coin. I fully agree with the Russian mathematical school that done a wonderful work, and I think that it is, especially in the case of spin glasses, it was very important because it was not clear if the thing is true or is not true. One may believe that it's true, but one thing is to give some argument, but other things have to have this really under control. And I think that having things really under control is something that is very important. Of course, sometimes physics is in advance of mathematics. Sometimes it's the other side. For example, for one thing, so string theory, Calabi-Yau invented the Calabi-Yau space before physics application. On the other hand, for example, Newton wrote the differential equation before one could prove in a rigorous mathematical way the meaning and so on. Dirac invented the Dirac distribution before people, Gelfand and other people discovered distribution theory and so on. So I think that the two things are going together. Mathematics is studying, in some sense, all possible worlds. Physics is just studying this world, but the input of physics is fundamental to have a new problem to study with for mathematics. For example, one example is the Kadar-Parisi-Zhang equation that describes the movement of surface. And the proof that the question makes sense is something quite not easy. Indeed, the guy that got the Field Medal, which is not important as the Hubble Medal as Lagrange, but is still a very important recognition.
Yes, KPZ equations are very famous.
Yes.
Dr. Bai,
Yeah,
anything to add?
Yeah, I think because we are engineers. I think how do you think math this should be very strict math to give a proof and fix. Somehow you need some some inspiration thinkings about a system.
That understand. I think that one should first things one should get is what we call physical intuition, which is engineering intuition. I mean, intuition of what the things are doing, what is the main point, and that is something that one. And after one should try to apply the type of mathematics that one has. And also, of course, what is very important is also probability, because you can use probability or things like that to cover the part that you don't have under control. But I think that it's very important.
The real system in practice is very, very complicated, just as your research areas. What's your opinion to use some physical thinking to help us to improve the design of our the very complicated systems?
For example, the things about Lagrange proof, it was important just to know that the argument could be justified in that particular case, and therefore you can use the same kind of heuristic argument in many other cases where you don't have the physical proof. However, the thing that is important is to try to understand the physics of the problem. This can be done with different ways, thinking about doing numerical experiment, proving try to understand how the system works in a strange situation and so on. So there are many ways you can do this type of things.
You know that the Nobel Prize in Physics of 2024 is awarded to John Hopfield.
Yes.
And Geoffrey Hinton for fundamental discoveries and inventions such enable machine learning with artificial neural network. This actually is a significant contribution of statistical physics to interdisciplinary fields. And what do you think are the key contribution physics has made to the development of AI, and in particular for large language model today?
Well, the Nobel Prize to Hilton and to Hopfield, I think, was a very important recognition, that also a statement on the nature of physics. Because one could think that physics could be limited to only traditional part of physics. It's clearly that the work of Hopfield is beyond the standard traditional part of physics, but I think that is good, because what makes relevant to physics, to discuss if something is physics or not physics, is to the type of technique people use. And it's not the type of subject, but the type of mathematical technique that you use, but that use mathematics in a deep way, not just counting and so on. And therefore, I think that this was very important. It was very important because we know that the idea of a neural network is quite old, and cybernetics was born in the 40s, and the perceptron was born in the 50s.
Yes.
But things were somewhat stagnant, also because there was not enough interdisciplinary connection. And the idea of Hopfield was twofold. One, going in the direction of recovering the connection with biology, with Hebrew rule and so on, as far as memory. And I think that was very important, that the think that it selected just one particular field, not all possible things of artificial intelligence, but some restricted field in which it could get the result. And also that doing this type of method, this model, one could bring all the techniques that have been developed in statistical mechanics also in this year, also the replica theory that they developed a few years before to study this type of problems. Indeed, often it was very clear that this model was a generalization of the Chaspark model that was used in spin glass. And also the Hilton idea was for which it got the Nobel Prize. The post machine was something that was very deep related to physics. Just the name Boltzmann.
Boltzmann machine.
Yes. Boltzmann
Yes.
machine, RBM. Yeah.
Yes.
It's something that comes from physics.
What roles can statistical physics tools play?
And now it's clear the large language model, I mean, all the field of deep neural network is something that one has to understand, because the point that we state that we have a very good understanding on one layer, a reasonable understanding on two layers, but we really do not have a complete understanding of
in the depths
of the system with many layers. Therefore, the fact that we do not have a deep understanding of a system with many layers means that we really do not have under control. For example, my understanding is that when one try to write to construct a deep learning neural network, one uses some phenomenological things of how much wide should be the network, how many connections, how deep it should be, but you don't have some first principle formula for which you could do the type of computation. The first principle formula that you have for the often modern memory.
Is it possible to develop an interpretability theory, or, for example, causal inference, understanding the logic for a large language model?
I think that this will be very important, because it's clear that you can do some simulations, but if you have you could know a priori these things, that this will be very important. And also there are many different variations of the model that you can think, and to have the difficulty is to find out first of all a well-defined problem, and also to do the computation, which is really tricky. But I think that I think that this is doable. I don't see any reasons for which one could not have a good thermodynamics and full mathematical understanding of deep neural network.
Yes.
And after that, one gets a deep neural network. Of course, the language is more difficult, but I think that one can try to make progresses in that direction. But I think that is something that will come out in one way or another one, because I always have seen that problems that looks very difficult, after sometimes some effort are solved. Of course, there's some problems that are not yet solved, but I hope that this will happen in the next future.
Yeah, actually, I have a few specific questions related to this one, because I learned from your work and your colleagues' work. You model the neural network, binary neural network is equivalent to some kind of set problems, and try to use the tools you invented to solve this problem. Because in that work, you consider the deep neural network is different from the transformer.
Yes.
If you think the transformer, can we use the same philosophy to solve to at the first step to solve the binary transformer something? Yeah, what do you think?
Yes. I think that look, I think that very important things is just to simplify the model in such a way
Yes.
that it can be analytic studied. For example, the Hoffman model was a very simple model because every spin or every neuron was connected to every other neuron.
Yes.
And the other things that was completely unrealistic from physiological viewpoint, that the neurons were effect of neuron A on neuron B was the same on neuron B that neuron A. That all kind of synapses were bidirectional. That the information could go in this way and the other way. This is completely opposite of what happens because of the information goes in one direction. But I mean, as usually people, once the Hoffman model was solved completely analytically, people start to study diluted model, what was happening if not all spins, or not all neurons were connected to all neurons, but only to a few one, to study what happens if the things were not bidirectional, what they start considered to study neurons that were much more complex than the standard neurons of the model, for example, the integrated firing neurons that are quiescent for a certain time, at a certain moment they fire. So the things, real things is to understand, to start from a model that is simple, to start to understand the simplest possible model, which is not too simple, but which have some connection to what you would like to understand, and for which you can do some kind of mathematical treatment. And after that you've done these things, you go on. And this is a whole history of physics based looking to simplify model to simplified model. For example, also Galilei at the beginning was studying a world without friction. But weather without friction is something that is very far from the real world because I could not keep these things this way without friction. Without friction, we slip down. So I was studying the world without friction, was a very strong success. So, however, if you want to do a model that is simple, but not too simple, still that you have a good understanding, intuitive understanding of what we want to study, and to see it from many different ways. You pointed that way that to construct a very simple model.
Yeah, another related question is about the Gardner capacity.
Yes,
it's a very, very important concept for the neural network, starting from the Hopfield network. And by now, we're trying to find a way to set up some equivalence between the transformer like attention scheme and the continuous variable Hopfield neural networks. We try to derive the capacity of that, but it's only related to memorize how much information, how much things you memorize by the neural network. Do you think this is enough for neural network? Do you think when you use ChatGPT, you think maybe he can derive something, not memorize everything?
No, not that I understand, but also one point that was very important. In principle, you would like to have some kind of network which does not only memorize but also classify.
Yes.
And that is a thing that is more difficult. I mean, there was a lot of discussions in the 80s with the late Miguel Vivasoro, because the thing that was thinking that most of the classifications that we are doing are hierarchical classification. We have said that what is living, not living, a plant, an animal. An animal is a mammifer, is a bird, is a fish, and so on. I thought you have the type of classification that you're doing are typical hierarchical classification. In spin glasses, you have a natural hierarchical scheme because the type of things that the state, the things that are hierarchical. So his idea was if we could do this hierarchical classification, we could help something to do in a neural network. In the framework of the model, this was not useful at all. But I think that maybe in other completely different situations, this would be useful. Because it's clearly that the way that we are thinking is we're using hierarchical classification. So if this could be derived, so that the network, the transformer, what else, tend to do some this hierarchical classification. The point that is crucial is that is learning for neural network or any type of network.
Yes.
It's learning from example.
Yeah.
Because there are two things that are crucial. One thing is learning, memorize.
Yes.
That I give you a certain number of examples and you memorize that one.
Yes.
The other thing is learning the rule by example. I give some example of addition. 5 plus 2 equal to 7, 7 plus 15 is equal to 22, and so on. And you ask to the network to learn the rule and to give the correct answer, also in the case where you have not known. And that is something that happens, of course, and happens quite easily for in certain contexts. But it's clear that in order to, this is something that is very important to understand how it happens, because you could try to do it with simple rules, but to understand in general. And understanding in general is not easy because, as I say, the problem is not well posed. Because I say that you have a rule, but of course, which kind of rules? There are so many rules, and therefore it's something that we like to understand. And I think that also the point is that if we want to formalize this in mathematical way, also we do not have a precise a way to define the rule and so on, apart from mathematical case and so on, addiction and other.
We previously discussed the value of statistical physics to the development of AI, in particular large language model. Leveraging this, we can have more exploration in the research of science. And how do you view this type of connection?
Well, I think that especially in this type of problem, understanding the behavior of a large number of agents, interdisciplinary contribution are extremely important. Indeed, the work, for example, that you mentioned that was done by Moser on place cells that recognize the neurons that recognize their position, is something that is extremely important both for the type of physiology, and also this led to lot of theoretical work of these things using Potts model, things like that, to statistical mechanics. There are a lot of statistical mechanics different models for which were extremely interesting that they should be used. And also the work that was done in chemistry that got the Nobel Prize of 2024, in which they were able to study protein folding. This was really something that was extremely unexpected, and they discovered a different part of artificial intelligence that is not related only with large language model, but the things that are using a different type of technology. Therefore, I think the work of Amari, continued work of Amari was very important. If you look to the paper of Amari of 74 and the paper by Offield of 82, they are not so different. But however, what is, if you just look to the formula, but what was different was the context in which the paper were put. And this is exactly because important, because when you put things in a different context, things are going to change. I mean, the work of Amari did not make any appeal to theoretical physicists, because it was something that was far from the things. There was not problem of capacity and so on. And while the fact that the Airfield was doing something similar, connecting more to biology that was not in the work of Ramari, connected with physics, with using Hamiltonian and so on, instead of Lyapunov function or things like that, which is not, and therefore this is something that is very important. And I think that in order to go on with the artificial intelligence, we have to use to better understanding also the brain physiology. The point is also quite clear that, I mean, if you look to the brain has 100 trillion synapses. A large language model has 1 trillion. So the things is very different. And however, the speed is completely different, because the speed of a computer, which are doing a large language model, is very, very high, while the type of clock of the brain is 50 operations per second. So we have more or less on the hardware, hardware capacity. It's not so, the distance is not so infinite as in the previous one, in the previous case. However, the capabilities are completely different, and it's quite clear that the way that the brain is going to learn the world is completely different from that one of large language model, because it's not done by infinite repetition of example and so on, and not just by backwards propagation. So it's clear that in order also to have some new progress from artificial intelligence, we need also some better understanding of how the brain works. And we are very far away, I think, from understanding how the brain works in many, many things. For example, one problem that I consider that is very interesting, but I've seen no problem in no studies, which is also not very different from the old problem of feed, is how our memory works, because of the point that we have at least two memory in the brain. A short-time memory, which may have 100 seconds or something like that, and we have a medium range memory. And now how the information is selected, moved from one memory to another memory, is something that we do not have a good model to move information around. And also there's some idea that maybe we have a way to store some information much longer, in which we may go from a short-time memory to a long-time memory, in which we select some information and we keep them information. How all these things is working? All this information storage of the things that you have memorized once is something that is extremely important. And that is something that we really do not understand, I think, at the present moment. Because it's not clear, because we know where the short-term memory in one part of the brain, we know the medium part in another part of the brain which is far away. Of course, attention, which is crucial for the transformer, is also important in this case.
Yes.
But there is something that also what is important, probably reinforcement learning, that you recall these things more than once, you try to, but how these things are going on is unclear. For example, many times people say that when you dream, you are doing some work to reinforce the memory in one region or another way, but this has never been proved in a way. And however, we do not have a low-level mechanism to select some information and move in the other one direction. Therefore, this is something that will be extremely important, because this is something that is fundamental for us, because the problem is that we have an incredible amount of information, and which we cannot memorize everything. For 100 seconds, we are going to remember the position of the bottom of the table and so on, without doing particular effort. But after, we are going to forget. So we are going to forget all the relevant details, and that how this is done is not clear at all.
Yes, and you just mentioned the use reinforcement learning. How about to use physics tools to get some scaling laws for the post training to evaluate how much inference capabilities we have just after some reinforcement learning method used in the...
No, it's a extremely interesting question, and however, we do, for the moment, we don't know how to do. And also, the scaling law you mentioned are more or less of a heuristic nature. They do not come from. I mean, you have seen how the things work with small systems.
Yes.
You do a power like fit and so on, but you cannot predict from first.
More or less very empirical.
Yes,
completely empirical. I mean, the fact that empirical is good, but because they are most likely correct, because they're empirical, but it's clear that one would like both to understand the origin, and also to understand if they how much will go the scaling law, if they will have a ceiling somewhere, or you don't have a ceiling, because this will be also very important from not only for theoretical viewpoint, but also for practical point.
Yes.
Because to have a neural network will be a factor 10 bigger than the present one would be extremely costly. And if you could change the prefactor, not only the spot, but the prefactor and so on, that will be much better. And also, you may arrive to a situation where you do something 10 times deeper, 10 times more bigger, and it does not improve so much. So to have a really understanding, that will be very, very important.
Yes, I see. And how do you think AI models can help the physicists to improve our physical research? Maybe it can provide us some new tools to find new physical laws or some new equations.
For physics, of course, it's clearly that, the distinction between chemistry and physics is not so deep. Therefore, computing and protein folding is something that was done by physics and chemistry. And, for example, the things that was done by artificial intelligence to doing this kind of business for protein folding will be extremely useful. And it's clearly that what artificial intelligence of this kind of type is able to find the hidden correlations that completely escape to humans. Therefore, I would be not completely surprised if you could do better earthquake prediction, for example, using artificial intelligence, because with earthquake we have a lot of information, so extremely detailed information of the infinitely many earthquakes that happens in one region. And this is something that possible could be extremely important to have a more detailed, to use some kind of models of artificial intelligence type to do predictions. And of course, that can be done. So, for example, we have many more thousand different electronic compounds which have a superconductor, different superconductivity transition from things, while the microscopic model is not completely clear at the microscopic level. And I think that artificial intelligence certainly could be able to predict, understand the behavior, the transition temperature of different systems. Of course, what would be more difficult is to do a microscopic theory of that. Would be completely different because it could not. There's a lot of things that cannot. I mean, the point is that artificial intelligence, as it is, does not have a knowledge of the world. I mean, it have no words, the different. I mean, that's not no reality. Therefore, for artificial intelligence, if you have a large language model, they can do wonderful things. They know, for example, replicate theory, they do the things, but however, they do not have a deep understanding what replicate theory is. Therefore, they can connect the world.
A causal inference, right? And
yes,
the logic.
Yes, they can do wonderful things. For example, I was in recent times I was using a lot of DeepSeek model, which I find that is much better than the other public model that were available. And however, there is all problem that I mean, they can do things quite well for physics because they know a lot of things of physics and so on. But the point that they are not able to do new connection, new things, because they do not have a connection reality. And the fact that there is no connection with reality is something that is, in certain sense, is some kind of limit of language model.
As far as I understand, statistical physics itself intersects with many disciplines from the perspective of communications and as well as coding, LDPC code, and also many other applications such as graph inference, discrete optimization, or a set problem, and so on. I think they are all rely heavily on statistical physics. And what's your view on this kind of interdisciplinary intersections, and as well as the intersection of science and engineering, and what value will this intersection bring to the development of science, and what impact will have it on the development of technology nowadays?
Yes, in the case of error correcting code, this is extremely interesting because I think it was my friend Nicolas Soulas and also with Helper Montanari that made the first observation. There was a deep statistical connection between error correcting code, and this was something that was extremely developed also by Riccardo Zecchina and others. And because type of computation are similar in some sense to the type of understanding the limit of memory capacity of a neural network, and to understand in which regions you may have some error correcting code which you can invert in a polynomial time, where you cannot invert, and the region for which you can invert in polynomial time is something that could not easily predicted in advance, but only by some numerical experiment or some very lousy upper or lower bound from mathematics, and that is clearly explained a priori, which is all the type of possibilities that you can do. how you can do error correcting code that works in a region that a very large number of errors that are very important, for example, for communication for faraway objects like things on Jupiter or far away from the space. And I think well, you see that as far as statistical physics in these days, it tackles the problem of dealing with a large number of agents. And the agents may be completely different objects. Maybe the agent, for example, the one that the piece of the code that they compress or expand the data and put in error correcting, and the piece of the code that extracts this type of information. So it's clear that when you ask the behavior of a large number of agents, there's all possible type of application that comes from every different region. And it's clearly that I believe that we only scratch the surface of this type of problem, because every time we go on, we find a new type of applications, a new type of idea. And also, the thing that is important to take care that you need a lot of time from the moment that you have a new idea to the moment where you apply it. For example, the idea of replica symmetry breaking in the 80s, it takes 20 years before to be applied to error correcting code, and the work of it was 84, backward propagation 10 years later, deep neural network, and end of just before 2000. But after, we need a lot of time before you have the success of image reconstruction that happened in 12, something like that. So it's clear that all this type of ideas, you have to develop new ideas, and the new ideas in this field takes a lot of time, sometimes, to be applied. Sometimes you have more or less instantaneous success as the transformer. The transformer was discovered, used on very, very fast. But sometimes you need a very long time. And I remember a story which is probably likely not true, but the story is very nice, that Faraday, at the beginning of the 19th century, were doing some experiment on electricity, magnet, and so on. The Prime Minister of England, I think Gladstone, went to see the laboratory, and he was showing that having some current here, the compass things was moving and so on. And Gladstone was interested, but said, look, everything looks very interesting, very new. But which will be the applications, all that? Faraday said, well, look, I don't know which will be the application, but I'm sure that in 40 years you will put some tax on the application.
My background is actually information theory. We think the physics provide us very powerful tools for engineers to rethinking the coding problem, like in the transmission or in storage. But besides these communication problems, we also think about how to use the physics tools to solve the set problems. I know you are expert in have many papers on that. Do you think is it possible to use physics tools to get new set solvers?
This is a very interesting question. However, it's something different and difficult. I mean, it's difficult to say in advance if something works or not. I remember that, for example, an ex-student of mine from Masorizzo did a very nice computation, and he presented the final computation, and I thought that it was lucky that he did not discuss with me the idea, because if I discussed with me the idea, I would have told him that it does not work, that it cannot work. And therefore, sometimes it's not easy to see in advance that things works. Of course, there was a very nice sentence by Weinberg, I think, that it says many times you try to do something that does not work, but you don't have to be sorry for that, because that's life. That once it works, but to find the one that works, you have to try it many times with something that at the end it does not work. So in this case, I don't know. It may be possible, but one needs a good idea.
Huawei highly values the role of basic research in driving industrial development, and has therefore established a theory research lab led by Dr. Bai, and the Lagrange Mathematics Research Center led by me. So from the perspective of a leading physicist like you, what's your view on the integration of industry, academia, and research, and how can we more rapidly translate advanced theoretical methods from the academic world into practical applications so as to boost industrial development?
I think that is very important what Huawei is doing in Europe with this center that you mentioned, because as I told before, research is very important. And what is crucial in research is that research is something that's communicated, that you have open research, because only if you have open research you can easy to do progress, because progress may comes from getting some idea from elsewhere, and all this network of people doing science, they basically communicate with them, one with the other one, and I think that this is very important. And what is I think that is crucial, especially in these days, because all practical, lot of practical industrial things is connected to more deep way to problems that are of scientific type. Therefore, we see that all in the construction of artificial intelligence, there's been a mixing of technique from theoretical physics, from mathematics, engineering, software, and so on. It's something that we have to acknowledge that this type, the industry becomes more and more relevant to science becomes more relevant to industry, in the same way that the industry becomes relevant to science. This is something that is important because, for example, industry, for example, if you want to understand how neural network works, it's clear that industry have incredible information how a neural network works, how you could do experiments, how you can test new ideas in different contexts, and so on. So I think that this is very important, and also I think that this is the type of collaboration of academia and so on important also for a problem that I think that would be very important for me in the future, for example, in the future artificial intelligence, that I think that would be very bad if in 10 years or 20 years, we finally arrived to only one industry that will make an artificial intelligence. Because I think that there would be very bad, because I mean, I don't think in the same way that we know that from at least on our side, in the Western side, that Google is the best research engine, and everybody use Google to do research. If we end that any type of artificial intelligence, we have a monopoly like that one of Google, I think that will be bad, because I think that especially for artificial intelligence, we need some kind of diversity, because otherwise there will be no innovations. And also, it's also a problem that with artificial intelligence, you have the problem of selecting the source that you put in artificial intelligence. And now, if there's only one machine that is doing artificial intelligence, one LLM machine, software, they have a power to conceal or not conceal everything to humanity, because they can decide to put this information, not to put that information. People will not, in the end, look directly on the web. Every done will be to do some given interface, and only having one interface will be very, very bad. So I think that having a multiple interface, it would be important. In order to have a multiple interface, you need some of the basic idea are somewhat common, part of a common knowledge, and therefore the idea that to have centers which with industry and academics, in which you can do open research on things related to artificial intelligence, something very important. And I think that this can be done in many different places. For example, we know the wonderful things that are done at Platinum by Huawei in Europe. But if we could have, for example, something of this type in Italy, in Rome, for example, we have a very strong statistical mechanics school, that would be wonderful, because I'm firmly convinced that the collaboration between industry and academics with open research is fundamental both for the industry, fundamental both for the academics, and also fundamental for humanity to have a monopoly. And to have one monopoly, I think that is something that we've seen in the past and so on, is not good, especially a monopoly with control information, like that one. I think that the most important interdisciplinary research comes out where people of some two different disciplines speak together.
Yes.
However, the things is not easy, because each people use their own language, and you have to do some effort to understand other people's language. For example, there was a wonderful book that was written by Mezzara and Montanari.
Yeah, I read that book before I pay you a visit.
And which is really doing a very strong effort to put a lot of results from physics in a language of that could be understood from different community. So having a center which people from different community may meet together, may discuss, they may present seminar, may give seminar, may present idea, having informal discussion at lunchtime and so on. All this type of communication is something that is very important, because the way that things are going on. Because, for example, I remember that I was in ICTP in Trieste, and to some conference, and at that moment Riccardo Zecchina, which I knew but not perfectly well, he had come to said, well, we can have lunch together and so on. And they started to discuss the problem of SAT model, to understand the K-SAT, all this type of computer science model. And that discussion at lunch was a trigger that helped us to go on in this direction with paper with Mezzar, Ricardo himself, and so on. But this was triggered by a discussion at lunchtime. And that was, and this is something that however, in order to have people who speak different language that speak together, you have to give some time to meet, to discuss, to present ideas, to have people that make effort on going one direction or another direction and so on. So center, which have doing interdisciplinary research, which have people both from the industry, people from statistical physics, people from mathematics, different type of field, is something that would be extremely important. Because sometimes people do not realize that there are some kind of similarities from what happens in one field in another one. For example, the things of error correcting code and so on was completely unexpected.
Maybe we can organize this kind of workshop, based on the Lagrange Center.
Yes. That we are going to do.
Yeah, we can invite different people.
Yes, we should discuss. We started to discuss with Federico Tianchi. We should go on to fix the details, the date, and so on, and the people to invite.
With different background, different problems.
Yes, exactly.
Very interesting.
Okay, thank you very much, Professor Giorgio Parisi.
It's our great honor to have this discussion.
Okay, it was a great pleasure because it was very interesting.